Oh,
I can do it.
no. Well, fine. Okay. I was gonna say, you're literally sharing the link.
All right. Yesterday, we were looking at particle motion a little bit further, but this time, how we can utilize an integral, okay, working backwards or area under a curve, to help us kind of analyze the motion of a particle. And I believe we left off on page 380, is that correct? With the graph? Okay, and we finished part A? Yes, okay. So let's go ahead and take a look at B. Maybe we'll reread it just so we're clear. The graph of velocity, measured in feet per second, of a particle moving along the x-axis is pictured below. The position at time 8 is 12. Use the graph to help us with some of these questions. All right, so we already figured out the position at 3, which was great. What about the acceleration at time 5? We have to think about...
I think it's negative.
Why is it negative? Well, at least we can anticipate something.
Because
So.
v of t is decreasing.
Okay, so they give us velocity, they're asking us about acceleration. That means we'd actually have to take a derivative or look at the slope of this graph. All right, so the velocity graph at this point is definitely decreasing, so we should anticipate a negative answer for sure. Can we figure out the number though?
-2.5.
How'd you get it?
That's the slope of the line.
Slope of that line. All right, so it looks like we go, if we pick a point before and a point after, we go down 5 over 2. So -5 over 2 or -2.5. Right as a fraction or a decimal. Can we put units on it?
Feet per second squared.
Good, feet per second squared. All right, what about C? What is the net distance, aka displacement, of the particle from 0 to 10? So they give us velocity, but they're asking us essentially about a position change, aka distance. So can we think about what we have to analyze about this graph to help us get there? Yeah.
The area under the curve.
Okay, aka an integral under this curve of velocity from 0 to 10.
Yeah.
Okay, so that's basically going to give us this change in position, aka displacement, how far you traveled on that interval. So if we shade it in, we need all of this area plus all of that area.
Yeah.
Can we use some geometry?
Yeah.
Yeah. Now, for our first shape here, we could utilize a trapezoid. Or if you wanted to, you could break it up into 2 triangles and 1 rectangle, whatever you're more comfortable with. It's completely up to you. Maybe I'll do trapezoid. So we have 1/2. The height would be 5. And my parallel bases have a distance of 2 and 6. All right, so then we have to add the area from this triangle piece, but notice how the triangle is underneath the x-axis, so it would actually be negative. And for our calculation, we'll have 1/2 times the base of 4 times the height of 2. Let's see, 8 times 5, 40, half of that, 20, half of 4 is 2, times another 2 is 4, looks like we get 16. Can we throw in units? Feet, okay. So when we look at the beginning point and the ending point at this time 0 and this time 10, we traveled 16 feet, okay, just beginning to end. D, on the other hand, is asking us something different, okay, total distance. So in this case, the direction we travel really does not matter. Can we set up perhaps another integral that represents total distance?
Absolute value.
And absolute value. Okay, we don't care if velocity is negative somewhere. All right, so can we think about how that would change this velocity graph if we took a or the absolute value of it? Go ahead, Austin.
Instead of subtracting that 4, you would add 4.
Right, so this little negative area is going to be flipped or reflected like that. So we're going to add up this area and then this new area. It's still 4, but now it's going to change to positive. So this would be 20 plus 4, which would be 24. Looks good. Now, if we look at the graph a little further, notice how this 20 is actually representing how much we move right, and then this 4 is actually representing how much we move left. So we can see like above x-axis, below x-axis to get that direction. Doing okay? I think we're doing great. All right. Instead of an equation like we did yesterday, and instead of a graph like we just did now, let's take a look at a table. Okay? So the table above shows velocity, meters per second, of a particle moving along the x-axis for some specific times. What does the value of the integral from 0 to 18 of velocity represent? If you were to figure out the area under the velocity graph from 0 to 18, what would that tell you about this particle? Good, Anush?
It's displacement from 0 to 18.
There we go. Net distance, displacement from 0 to 18 seconds. So if we think about the fundamental theorem of calculus, if we work backwards from velocity, that would represent position. And if we know the bounds, we would have 0 to 18. And if we did top bound minus bottom bound, notice how we're taking an ending position minus a beginning position, so that would give us displacement. So the area under velocity represents the change in position, meaning some distance value. All right, so let's see if we can maybe estimate, because we have a table, what this displacement might be. And we have talked about several different ways that we can estimate the area under a curve. So we're actually going to review all of them. We're going to do a left, a right, a midpoint, and a trapezoid. All right, so we'll put in little squiggles. For part B, we want a left Riemann sum of 6 subintervals. So maybe break up the table into 6 pieces. Or let's see, we're going to do some rectangles here. So from 0 to 3, that'd be a base of 3. What can we use as our height value? 2.3. Good. We want the left-handed side. All right, so we're just going to repeat the process all the way through. Looks good. All right, so 6 areas that we got to add together. Go ahead and take the time to type it in to get our estimation. Anybody get it? Maybe quick fingers. I know Addison's not here to carry our backs like he normally does.
I love it. Wow.
33 units. Meters. All right, so There's one approximation for this displacement, just based off the table values that we know. Let's see if we can get another approximation. This time we'll do a right Riemann sum. So it's going to be very similar. We still have the 6 subintervals, or those 6 rectangles. Our base length is still 3, but this time we want to choose the right endpoints. So that'd be, let's see, 2.7, 2, 1.3, 1, 1.7, 2.1. 1, 2, 3, 4, 5, yep.
32.4.
32.4 meters. All right, so that's another approximation. It would be wonderful if we knew kind of the behavior of this velocity graph. Like, is it concave up, concave down, increasing, decreasing at some spots? If we knew that information, we could probably determine if these are over or under estimates. But for right now, we'll just take them at face value and say that they're an approximation. D, on the other hand, is a midpoint, and they only want 3 subintervals. So we're going to have to change our rectangles here. This time, our base is going to be 6 units, and we're going to want to use the middle height. So that'd be 2.7, 1.3, and 1.7.
34.2.
Wow, 34.2.
You are so good.
Addison 2.0.
Stu says nothing.
All right, for part E, by the way, can we get the, I know Austin's doing it very quickly, but can we get those numbers?
Yeah.
Yeah, okay.
Action,
It's actually, he's just whispering it over.
yes,
Okay.
them back and
All right, E, using a trapezoid of 6 subintervals. So we're going to have to go back to the 6. Let's see. Estimate the value. So what's our formula for a trapezoid? 1/2 times the height times the sum of the bases. Okay, so let's just look at our first one here. Can we label what the height would be?
3.
3.
Why 3? That's good. It's a sideways trapezoid. So the height is actually on the x-axis. It's going to be that 0 to 3 distance. And then the 2.3 and the 2.7 are your 2 parallel bases when you draw your trapezoid on a graph. All right, so we're going to repeat this process all the way through.
Actually, calculates a lot of two values.
First one, so right now. Approximately 32.7.
I concur. Looking good?
Amazing.
Amazing. Perfect. Okay. Let's keep going. Find the average acceleration of the particle from 3 to 9. For what value of t in the table is this average acceleration approximately equal to the derivative of velocity? Let's see. Average acceleration, how is that related to velocity? Because that's the table we have up top. The slope. Okay, so we want the slope from time 3 to time 9. So we're going to use this point and this point. So we need the change in y's over the change in x's. It's definitely going to be negative. And less than 1. Negative point.
1, 5, 6, 4.
We just made it up? Well,
0.2333.
yeah, I got 0.2 something. Minus 2.7
0.4.
divided by 6.
Oh, nuts.
Yeah. 3, 3, 3. Could we put in units?
Minus 3 is 6.
Meters per second.
Yeah, I times it.
Meters per second squared. It's an average acceleration. Okay, so for what time in the table is this a derivative value or approximately a slope value?
6.
Why? Good.
Because it would be the tangent line for 6, right?
Yes, okay. Why 6?
Because you're taking the points on the left and the right.
There we go.
So the slope would be close.
Close to it. Okay, so one of our ways to approximate a derivative is to pick a point before it and after it. And notice how that would approximate a derivative of 6 based off the table that we have. So t equals 6 because we found the slope from 2 points before and after. Okay, this is essentially the mean value theorem in a sense, where the average rate of change, that AROC, is equal to the derivative, meaning instantaneous rate of change. It's kind of that same concept, where we're finding the slope between 2 points on either side to help us approximate a derivative somewhere in the middle. So I like that. All right, look at the last one. This one's going to be a thinker. Explain what this integral means in the context of the problem. Now, we already said what the main integral part was at the very first question at the top. We said that was displacement, like how far you travel on some interval. What do you think would happen if we multiply by, for instance, 1 over 18 in this case? You have an idea,
That's a
Noosh?
good question.
I know.
It represents the average, like, feet you travel in, like, per second.
So average feet per second would be average velocity, okay? How did you know that? That's great.
Because if, like, the integral from 0 to 18 of v of t
Mm-hmm.
is, like, the total displacement,
Mm-hmm.
then, like, dividing by 18, since there's 18 seconds, you have kind of like the average.
Okay.
Instantaneous.
Look at this. If we already know if we were to work backwards from velocity, that would represent some change in position. Okay, position at 18 minus position of 0. But if we're multiplying by 1 over 18 in front of the integral, that means we have to multiply this change by 1 over 18 as well. And perhaps maybe I'll rewrite this. Instead of multiplying by 1 over 18, that's the same as dividing by 18. Now, what did you notice was special about the 18, though, Anuj?
Because there's 18 seconds total, so it kind of represents,
Right. So notice how the bounds on the integral from 0 to 18 are represented by this 18 in the denominator. Okay, this is the difference of the bounds. Okay. So if you're taking a change in position, which we know is a unit of meters in this case, and you're dividing by 18, which represents a difference in the bounds. From the table, the bounds come from the time, which would be seconds. Okay, you're getting a velocity value. So if this is the average change in position, okay, displacement, then you're going to have an average velocity in the end. So this is your average velocity. Okay, so this is going to kind of lead us into an additional way to find average values. Notice how we were able to use 2 points from velocity to find average acceleration. And up to this point, we would have to know 2 points on position to help us get average velocity. We don't have any position points available to us. We just have velocity points. So we can now include an alternative method to find an average value by utilizing an integral. And that's what we're kind of going to explore on this back page. All right, so we're just going to revisit kind of average velocity, average acceleration, how we can calculate those, but depending the information that we have available to us. So at the top, they're giving us a position function moving along an x-axis, units, meters per second, time interval 0 to 5. All right, now if you look at 1 and 2, we're going to find the average velocity for both of them, but we're going to find it a different way, utilizing either the position function or a velocity function. Okay, so depending on the information you have, it's going to dictate kind of the method or the process or the calculus that you use. So how can we find average velocity if we know position? Yeah?
Plug in the bounds to get where each one starts and ends and whatever. And
Yep.
then you slope.
You slope them. There you go. All right, so if we plug in 0, we'll get -9. Take a moment and plug in 5.
Definitely 46.
No.
There's a 46 in it.
346.
346. Okay, so we have 2 points on position. We know average velocity is the slope between 2 points on position. So we'll slope these numbers and 71. Can we put units? This is a velocity. Yep, average velocity, meters per second. All right, now we already know what our average velocity should be, but let's see if we can get the same result, this time by utilizing a velocity function. How can we figure out the velocity function? Derivatize position. So 9t squared minus 4t plus 6. Okay, so in order to find average velocity using velocity, we're going to have to use that integral concept. Our bounds are from 0 to 5. We're going to utilize our velocity function. Now, if we left it like this, this would give us displacement, okay, our change in position. But to find the average velocity, we're going to have to multiply by 1 over the difference of the bounds, symbolizing that second unit that we have. So the difference between the bounds would be 5. Okay. Now, I want you to just type this in on your calculator for time purposes. So we'll go ahead and type in 1/5. And then we'll use Math 9 for our integral. And notice how we'll get 71. Okay, so depending on the information we have to be familiar with which setup or what type of calculus to use. Are we simply finding a slope between 2 points, or is there some type of derivative or integral involved? Okay, depending on the information we have. Yes?
Mine's not a stupid question, but I'm just kind of confused.
Sure.
So like that thing on the left, the 1/5 times, and then the integral.
Yep.
Like whenever we say equals, on the right side of equals, if we weren't to use a calculator, we just do the thing that we did up top, right?
Essentially, yeah, because if you did this by hand, if you worked backwards, you would get the position function. The thing is, though, you don't need the plus c because you know your bounds. And then all of this would be divided by 5. So if you do top bound minus bottom bound would end up being 0, plugged in all those. So if you plug in 5 for all these, divide by 5, you're going to get 71. Yep. If you were to do it by hand. All right, let's try the same thing, but this time we're going to look at average acceleration. So depending on the information we have, we're going to first take a look at if we had velocity, and the second one we'll take a look at if we actually had acceleration. So assuming we have a velocity function, which we actually found in part 2, how can we use that to get average acceleration? We know.
Derivative of that, and then do the same. It's the same thing, just with the antiderivative of the velocity.
All right, so that's gonna be for number 4, because you're finding the acceleration function. How can we strictly use velocity to get average acceleration? Yeah. No. Okay, velocity for 0, velocity for 5, and then we're going to slope those 2 points. So plug in 0 to velocity, we'll get 6. If we plug in 5 to 11, all right, so then slope those. (41). Okay, units, if this is an average acceleration, close, meters per second squared. All right. So we're going to approach average acceleration again, but this time we're going to assume that we only know the acceleration function. Now that involves us finding it, but we're going to use that function to help us. So we have velocity. If we take the derivative of that, we'll get 18t minus 4. So we're going to use this function to help us eventually get the 41 average. So we're going to integrate acceleration. So this, if we left it the way it is actually representing the change in velocity value as that antiderivative. But if we want average acceleration, we're going to need to multiply by 1 over the difference of the bounds, which would be 5. All right, so again, time purposes, we'll type it in. And we get 41. All right, so we're just kind of adding to our Batman utility belt, I guess, with techniques that we can use to help us approach different types of scenarios. Whether we want to find average acceleration or average velocity, it depends on the function or the information we know. We doing okay?
Yeah.
Sound good? Alright. Alright, so we'll end there for today, and we'll start our next section on Monday. Actually, no, we have a free response day on Monday. I told you we'd be doing more of those. Free response on Monday.